I want you to start by picturing a standard ceramic mug sitting on your desk. You've just poured a fresh, hot cup of coffee.
Right.
You turn away for, what, maybe 10 seconds, check a notification on your phone,
Yep.
and when you look back, the cup is empty.
Which is usually a sign I've had way too much caffeine and just drank it without even noticing it.
Usually, yes. But in this scenario, there's a puddle on the desk. You didn't knock it over.
Okay.
The coffee actually climbed up the inside of the mug, rolled over the rim, crawled down the outside, and dripped onto the table.
That is a physics nightmare and a literal mess.
It is. Thankfully, coffee doesn't do that. But there is a substance that does exactly this. We are talking about helium, specifically superfluid helium.
Ah, the stuff that breaks almost every intuitive rule we have about how matter is supposed to behave.
It really, really does. And to guide us through this weirdness today, we're doing a deep dive into a paper by Jerry Z. Liu titled Superfluids Are Not Fluids.
Which is a great title.
I have to admit, when I first saw that, I thought it was just clickbait.
It does sound like a contradiction in terms, doesn't it?
Right.
I mean, if it flows, it's a fluid.
Yeah.
That's the definition.
Right. But Liu is making a really compelling and I think fundamental argument here. He's saying that what we call a superfluid isn't just a liquid with superpowers.
It's something else entirely.
Yeah, he argues it's a collection of unbound atoms that have, and this is the key, absolutely zero attraction to one another.
And that distinction, unbound, that's everything. It suggests a superfluid is less like a liquid and, more like a gathering of people who've all agreed to just completely ignore each other.
A liquid of extreme introverts.
The ultimate introverts. And because they ignore each other, things like friction and gravity and containment just stop working the way we expect them to.
So, okay, let's unpack that. To understand why Liu says it's not a fluid, we have to agree on what a fluid actually is.
And I think for most people, the defining characteristic is viscosity.
Viscosity, right. The resistance to flow. Honey is high viscosity, water is
Yeah.
low. Now, I always thought of viscosity as like friction, molecules bumping into each other in a crowded hallway. The more they bump, the slower they all go.
That is the common intuition, yeah, but it's actually the opposite. In the quantum world, molecules don't really like bumping into each other. They repel if they get too close. Viscosity isn't about collision.
It's not.
It's about attraction. It's cohesion.
So it's not people bumping shoulders, it's people holding hands.
Precisely. In a normal fluid, like that coffee, the molecules are chemically attracted to their neighbors. They want to stick together.
Okay.
So when you pour it, the molecules are literally clinging to one another, resisting the motion. That drag is what we measure as viscosity.
Okay, so stickiness equals viscosity. Now this is where helium comes in. Why is helium the chosen one for breaking this rule?
It all comes down to its atomic architecture. Helium is just incredibly simple. It's small, it's symmetric, and it's a noble gas.
Meaning it has a full outer shell of electrons. It doesn't need to bond with anything.
It's chemically aloof. It ignores most of the sticky forces that hold other liquids together, like the hydrogen bonds in water. The only thing holding liquid helium together is something called the London dispersion force.
The London dispersion force, that sounds like a British police squad.
It does, doesn't it? But it's actually the weakest intermolecular force there is. It's caused by the electrons in an atom just sort of wobbling.
A wobble.
Yeah, even though helium is symmetric, the electrons move around. For a split second, they might be on one side of the atom, creating a tiny, temporary negative charge.
And that little charge attracts the neighbor.
Just for a moment, that wobble creates just enough attraction to keep the helium atoms together as a liquid. That's why at, say, 4 Kelvin, liquid helium is still a normal fluid. It has viscosity.
But then we cool it down, we take it down to the lambda point, which is about 2.17 Kelvin, barely above absolute zero. What happens to that wobble?
It vanishes. At the lambda point, the thermal energy drops so low that the electrons settle into their absolute lowest energy state. They just hug the nucleus. They stop wandering.
And if the wobble stops?
The London dispersion force disappears. The glue is just gone.
So Liu's argument is that at this point, the atoms aren't just slippery, they are completely chemically independent.
Correct. They are effectively unbound. They don't attract their neighbors. They don't drag each other along. Viscosity drops to zero because the mechanism for it, cohesion, have been switched off.
That is wild to think about. If I stir a cup of coffee, the swirl eventually stops because of friction.
But if you stirred a cup of superfluid helium, that vortex would spin forever. Literally. Indefinitely. There is no internal friction to stop it. It's perpetual motion in a cup.
So the paper mentions a specific visual experiment that proves this is happening, and it involves boiling.
This is one of the most dramatic demonstrations in all of physics.
Yeah.
Imagine you're in a lab, looking into a transparent door, a high-tech thermos full of liquid helium, and you're cooling it down.
So it's boiling.
Violently. It's churning. Bubbles are rising everywhere. It looks chaotic.
And then you hit 2.17 Kelvin.
And in a fraction of a second, it stops. The boiling completely stops. The liquid becomes perfectly still, like a solid block of glass.
That's spooky. Why does the boiling just stop like that?
Well, think about what a bubble is. It's a pocket of gas trapped inside a liquid, right? But for a bubble to exist, the liquid has to have surface tension.
The molecules have to pull on each other to form a skin around the gas.
Right. And surface tension is just another form of attraction.
Ah, I see where this is going.
So at the lambda point, when that attraction shuts off, surface tension vanishes. You can't form a bubble if the liquid refuses to hold a shape. The gas just slips out effortlessly. So the violent bubbling is replaced by this eerie, silent evaporation just from the surface.
I want to dig into a nuance here from the source. Usually we learn phase transitions happen at a specific temperature. Ice to water, 0 degrees Celsius. It's a sharp line.
Right, a first-order phase transition. The temperature stays constant until the change is complete.
But Liu argues the superfluid transition is different. He says it's not a point, it's a range.
This is a fascinating part of his argument. He looks at the specific heat curve. The graph is how much energy the helium absorbs as it cools. It forms this sharp peak that looks like the Greek letter lambda.
Hence the lambda point.
Exactly. But the curve shows that the helium starts absorbing massive amounts of energy before it hits 2.17 Kelvin. It starts around 2.6 Kelvin.
So what does that mean?
Liu interprets this as the bonds breaking gradually. It's not a light switch flipping off. It's more like a crowd slowly dispersing.
So at 2.6 Kelvin, the first few atoms break free and become superfluid atoms.
They become loners. As you keep cooling, more and more atoms join the loner club. The 2.17 Kelvin mark isn't the start of the change. It's the finish line. It's the moment the very last pair of atoms lets go.
So for a short time, you have this hybrid, liquid part normal, part superfluid.
That's the theory. And it would explain why that specific heat curve looks the way it does. The energy is being used to break those bonds one by one.
Okay, so we've established what this stuff is. A collection of unbound atoms. Now we have to talk about the creeping coffee. The wall climbing trick.
The roll-in film, yes. This is the classic party trick of superfluidity.
So we have our superfluid helium in a glass beaker. Gravity's still a thing, right? It should be keeping it in the cup.
Gravity is definitely still pulling down. But to understand why the helium ignores it, we have to look at this three-way tug-of-war happening right at the wall of the glass.
Okay, so let's break down the players. We have a helium atom right next to the glass. Player 1 is gravity pulling it down.
Correct. Player 2 is adhesion. This is the attraction between the helium atom and the glass wall itself.
The glass is pulling on the helium.
Yeah, the glass has little electric charges on its surface, and the helium atom is slightly attracted to those. This is a Coulomb force pulling it up and against the wall.
Okay, so gravity down, adhesion up, and player 3.
Player 3 is cohesion. This is the rest of the liquid helium, all the other atoms, trying to pull that one atom back into the group.
But we just established that in a superfluid, cohesion is 0. The group doesn't care if the atom leaves.
Exactly. And that changes the whole equation. In water, cohesion is strong. So gravity and cohesion together easily win against the wall's pull. The water stays in the cup.
But in superfluid helium, cohesion just walks off the field.
It's gone. So now it's just a one-on-one fight, gravity versus adhesion. And it turns out the electrical pull of the glass wall is way stronger than gravity.
So the wall is pulling the atom up, and there's no friend pulling it back down?
So the atom just rushes up the wall. And because there's no viscosity, no friction, it builds up momentum. It climbs right up the side over the rim and flows down the outside.
And it acts like a siphon, draining the whole beaker.
It essentially tries to spread itself into a layer that's just one atom thick over the entire available surface, completely ignoring gravity.
That really does sound more like a gas that happens to be dense rather than a liquid. It just fills the space available to it.
And that's a strong argument for Liu's thesis. Liquids are defined by cohesion. This stuff behaves like it has none.
Okay, speaking of slipping through places, let's talk about superleaks.
This is a great proof of the unbound theory. You take a container with a porous bottom plow, something with nanopores, tiny holes about 0.7 nanometers wide.
Incredibly small.
It is. If you put normal liquid helium in there, it won't drip through.
Why not? Is it too fat to fit?
In a way, the viscosity prevents it. The atoms stick to the walls of the pores and to each other, and they basically create a clog. It's too sticky to squeeze through.
But the superfluid.
The superfluid atoms have their electrons in those low, tight orbitals, so they are effectively smaller. But crucially, they don't stick to anything. They just slide right through. It's like pouring sand through a tennis racket.
And this mechanic, this leads to the fountain effect, which, I have to say, sounds like straight-up magic. A pump with no moving parts.
It's a thermodynamic pump. It's brilliant. So imagine a tube dipping into a bath of superfluid. The bottom of the tube has that porous plug we just talked about.
Okay, so superfluid can slip in and out easily.
Right. Now, inside the tube, we add a little heater. We warm up the helium inside just a tiny bit.
So we push it above 2.17 Kelvin.
Exactly. We break the superfluidity. The helium inside the tube turns back into normal, sticky liquid helium.
Okay, so now we have a tube of sticky helium sitting in a bath of slippery helium. Why does that make a fountain?
It's all about the balance of forces. The sticky helium inside now has cohesion. It wants to grab things. The superfluid outside has no cohesion.
So the sticky helium grabs the slippery helium.
It effectively creates a one-way valve. The sticky molecules inside can't fit back out through the tiny pores. They're too fat and sticky. But the slippery superfluid outside can still rush in.
Ha, got it.
The sticky helium inside pulls on the superfluid below it. It creates this osmotic pressure gradient, and the superfluid rushes in to try and equalize things.
So the heater acts like a piston, pulling more and more in.
Precisely. The pressure builds and builds until whoosh. It sprays out the top of the tube like a fountain. You're converting heat directly into mechanical lift.
Just by playing with the stickiness of atoms.
It's so elegant. No gears, no pistons, just quantum mechanics doing the heavy lifting.
Now, I want to pivot to a part of the paper I found really compelling. We've been talking about helium-4, but there is another isotope, helium-3.
The lighter, rarer twin.
And this is where the theory gets a serious test. Helium-4 turns superfluid at 2.17 Kelvin, but helium-3, it won't do it until you get it down to 0.00025 Kelvin.
That is nearly 1,000 times colder. It's tantalizingly close to absolute zero.
So why the huge difference? They're both helium. They should be chemically the same, right?
This is where we have to look at the nucleus itself. It's a geometry problem. Helium-4 has 2 protons and 2 neutrons.
It's stable, symmetric.
Right. It forms a perfect tight little sphere. So the electron cloud around it is also a perfect sphere. It doesn't wobble much, which is why its London dispersion forces are weak. It turns superfluid pretty easily.
But helium-3?
Helium-3 has 2 protons, but only 1 neutron. It's unbalanced.
Asymmetric.
Those 2 protons repel each other. And with only 1 neutron to hold them in check, the nucleus gets stretched out.
So the nucleus isn't a sphere, it's more like an oval.
Exactly. And because the nucleus is elongated, the electron cloud around it gets distorted too. It also becomes an elongated oval shape.
And I'm guessing an oval wobbles more than a sphere.
Much more. The electrons are more easily disturbed. This means the London dispersion forces, the stickiness, are significantly stronger in helium-3.
Ah, so helium-3 is just naturally much stickier than helium-4.
It is. The atoms cling to each other much more tightly. So you have to remove almost all the thermal energy to get those electrons to finally calm down enough to stop attracting each other.
That's a beautiful connection. The literal shape of the nucleus dictates the macroscopic behavior of a bucket of liquid.
It really validates Liu's unbound theory. If it was just about something else, the mass difference shouldn't matter this much. But if it's about breaking intermolecular bonds, then the strength of those bonds is everything.
Okay, so we've covered liquids that act like gases, but we have to talk about solids. The paper brings up a paradox here.
The freezing problem, yeah.
Right. If a superfluid consists of atoms with 0 attraction to each other, how can you ever freeze them? A solid needs atoms to lock together.
It's a legitimate logical trap. If there's no glue, there should be no solid. And in fact, at normal pressures, helium will never freeze. You can cool it to absolute 0, and it stays liquid.
The only element that does that.
Correct.
Huh.
But we can make solid helium. We just have to cheat.
We squeeze it.
We apply pressure, about 25 atmospheres, and Liu proposes a specific mechanism for what's happening, which he calls the compression bond.
Okay, so how is a compression bond different from a normal bond?
A normal bond usually involves sharing electrons or natural attractive forces. A compression bond is forced. Imagine those helium atoms again, ignoring each other. But then you start shrinking the room they're in.
You force them into each other's personal space.
You squeeze them so hard that their electron clouds physically deform. They get squashed out of their nice spherical shape.
And when you squash them?
You create artificial positive and negative poles. You induce dipoles. And those forced dipoles lock the atoms together into a solid structure. The moment you release the pressure, the electron clouds spring back, the attraction vanishes, and it melts.
This sounds like it has implications way beyond helium.
Huge implications. The paper suggests this compression bond is the same mechanism behind metallic hydrogen.
The stuff inside Jupiter, the holy grail of high-pressure physics.
Exactly. We've struggled to understand how hydrogen gas becomes a metal at the core of gas giants. Liu suggests it's the same story. Extreme pressure deforms the atoms, creating these bonds that let electrons flow freely.
So studying this weird little liquid in a cup might unlock the secrets of planetary cores.
Physics is all connected like that. The rules that govern the very small usually govern the very, very dense.
It really reframes how we think about matter. We assume solid, liquid, gas are these fixed categories, but this paper argues they're just descriptions of how much the atoms stick together.
It just strips away the labels. Matter is a balance of forces. Attraction versus thermal energy. When you turn off the attraction, the categories just fall apart.
Which brings us to the final thought experiment in the paper. And this one really stuck with me. We've all seen videos of astronauts on the ISS playing with water.
Floating spheres of water. Yeah.
Right. You squeeze a water pouch, and a perfect wobbling sphere of water just floats there. We take that for granted. But why is it a sphere?
Surface tension, cohesion. The water molecules are all pulling on each other, trying to get as close to the center as possible. The sphere is the shape of maximum togetherness.
So here's the question. If an astronaut on the ISS released a bag of superfluid helium into the cabin, what happens?
It would be like a ghost.
It wouldn't form a sphere.
It couldn't. There's zero cohesion, zero surface tension. There's absolutely nothing pulling the atoms into a group.
So without gravity to hold it in a cup, and without cohesion to hold it in a ball.
It would simply disperse.
Yeah.
It would expand outward like a gas, separating into a fine mist of individual atoms, just dissolving into the cabin until the atoms were so far apart they'd never touch again.
That is a haunting image. A liquid that only exists because we force it to stay in a container. The moment you remove the boundaries, it just chooses to be nothing.
It's the ultimate unbound state. It challenges our whole concept of what a substance even is.
Well, on that existential note, I think we'll leave it there. I'm going to go check on my coffee and be very grateful for the hydrogen bonds holding it in the mug.
Cherish the viscosity.
Thanks for diving deep with us. We'll see you on the next one.